So I'm very excited to be here, even virtually, to present some of our recent research. So the title is Building Generalist Robot with Agility via Learning Control, Humanoids and Beyond. There are two keywords. One is generalist, another is agility. We will go to detail later. And here are some teaser videos, like some research I'm going to highlight today. And the first one is humanoid whole body control. We translate human motions to humanoid motions. And the second one is a sampling-based model product control method for contact-rich problem called DIAL-MPC. And the third one is our recent work on kind of real to sim to real reinforcement learning for learning whole body control, agile whole body control for humanoid. Um, okay, let's get started. Let me start by some recent trends in general purpose robot. Seems like general purpose robot, especially humanoid, are taking off, right? And this is just like a partial list of humanoid companies. There are also a lot of big players like NVIDIA, Tesla, Amazon, Meta. So what is general purpose robot? And many different people have different definitions. So my definition is pretty simple. That is a robot that can do many different tasks in many different environments. For example, here are some humanoid skills from my lab using the Sim robot, Unitary H1. You can see the top left, the robot can play tennis. This is the teleoperation. It's a whole body control playing tennis. And on the bottom left, a robot can interact with human, give my student a handshake, uh, and give my student a hug. So this is not teleoperation. This is autonomous powered by GPT-4o at that time. You can see we are waiting for the API's response. This human-eye-human interactions. Uh, and also say hi, say bye. And on the top right, each one can do some interesting local manipulation task and move one basket to the cart and move another basket to the cart and move the cart. Yeah, this is like a teleoperation local manipulation problem. And the bottom right, the H1 robot can do some pretty funny clamping dance. This is from the WoCoCo paper, and this is also like autonomous. So basically, my point is, it's pretty cool to see a single robot can do so diverse tasks, right? From dancing to local manipulation to playing sports to human interactions, right? So I'm not trying to see like only humanoid can do this, but a good thing about a humanoid is general purpose, right? It can do many tasks simultaneously. And another perspective of general purpose robot is robot that can learn from diverse human data. This is another advantage of general purpose robot, especially humanoid. For example, this is our recent work collaborating with Professor Xiaolong Wang's group at UCSD. This paper is called Humanoid Policy to Human Policy. You can see in this video, the diagonal term is robot data, the humanoid data. The non-diagonal terms are human data. So we can learn a shared representation. We can learn a shared policy in a shared representation space, and we can easily transfer a human policy to humanoid policy, right? This is also some advantage probably only humanoid has. For other robot, you in general need to solve a pretty non-trivial retargeting problem, or yeah. So yeah, this is like the definition. And what is the challenge? I think, in my opinion, there are two different aspects defining useful general purpose robot. Where the x-axis of this figure, the brown axis is the generalist aspect, or like the bright in task and environment diversity, right? Like for example, like for humanoid, there could be how many different terrains it can handle, right? And how many different kitchens it can handle, things like that. And the y-axis, the green axis here, is something I refer to as agility aspect. In general, it refers to depth in task execution. I abuse the word agility a little bit because agility here is not just like speed, right? It's also something like dexterity, precision, safety, reliability, this kind of thing. In general, it refers to how well the robot can achieve this task. So ideally, we want something like this, right? plot here, right? We want a robot that can do many, many different things in many, many different environments, all better than human performance in terms of agility, right? The blue dashed line here is a human performance, right? So it sounds very hard because we want to boost breadth and depth. But an interesting fact is, seems like in other community, like especially natural language processing, right? Large language models have roughly achieved this already. If you think about like large language model, right? A single model, a single neural network can outperform classic method and human in many different tasks simultaneously, right? Like 10 years ago, we used to have different method for different tasks in NLP, right? For machine translation, summarization, sentiment analysis, etc. But now we just have a single model. So here's interesting question, right? How far away from achieving this in robotics, right? How about robotics? Can we cover both generalist aspect and agility aspect? And there seems to be some trade-offs. We're making progress, but there seems to be some trade-offs. On the one hand, right, there are many amazing works focusing on agility in some specific task, primarily in the control community, right? But however, with limited generalizability and corresponding to this figure, that basically means, right, the method on this robot works really well for one or two tasks, but you cannot really ask it to generalize. For example, let me start from some work at CMU. Back in 1990s, almost 35 years ago, right? Professor Chris Atkinson and Stephen Shaw already achieved this humanoid ball juggling, right? And keep in mind, this is 35 years ago, right? It's vision based. It's a first person view. You can see. I think it's still impressive until today, right? And this is double stick juggling, even harder than ball juggling. I cannot do this. Yeah, I'm not sure if you could or not, but it's pretty hard. And again, it's 35 years ago. I'm sure if today any humanoid startup released this similar video, people will claim humanoid is soft. Anyway, this is 35 years ago. And this is another very famous examples from the very famous Ishikawa lab in University of Tokyo in Japan. This is like high-speed pen spinning. I want you to pay attention to a few seconds of the video because it's so fast. The motion will blur. You can see here, right? The tripod robot, three-finger dex hand, can like in hand rotate the pen very fast. And this is a slow motion. You can see the three fingers coordinate with each other. They basically have everything we have today, right? They had tactile sensing, they have vision feedback, yeah, and they designed like some model-based approach. Another example, I'm sure everyone here probably know this, is the parkouring from Boston Dynamics Atlas, right? Of course, this is like the old Atlas. And this is still, right, one of few humanoid that is physically more capable than human. Yeah, so beautiful. Very agile motion, very smooth, right? Again, this is solved by offline trajectory optimization plus online model predictive control. There's no learning. Okay, but the question is, how about here, right? What are these method performance for something like here, right? If you ask the method to generalize, right, what happens? Right, we have something like this, right? And the same robot that can do parkour can also make this very interesting mistake, right? In this video, what happens is Atlas thought it caught the cart, but it actually didn't caught the cart, right? And this weird feedback loop makes it fall, right? I guess you probably will not argue with me. This task is much easier than parkouring, right? But in reality, right, it may be hard for parkouring for robotic atlas, right? Um, okay. On the other hand, right, let's go to the generalist world corresponding to this figure, right? We have been making a lot of progress in the generalist world, especially after 2022, after like the GPT moment, right? Corresponding to this figure, basically means like the system can do a lot of amazing tasks, but the performance is still kind of suboptimal. This is a little bit outdated, but examples like this is an example from Google called Robotic Transformer series. And today we have like better system like Gemini Robotics from Google, like Groot from NVIDIA, right? And the Helix from Figure. You can see in this video, like a robotic transformer can do many different tasks in many different environment. Yeah, it's thousands of tasks. But I guess you probably will not argue with me, right? This task pretty much focus on pick and place, number one. And number two, they're not very agile, right? For example, like picking up a Coke can takes like a minute or 30 seconds, right? I don't think you want to spend $1,000, right? For some robot that give you a Coke can in like in a minute. You want something agile, right? As agile as you. So many of these methods I mentioned, like Gemini robotics, like this robotic transformer, like Helix Groot, they're basically following a learning from demonstrations pipeline, right? You collect a lot of human data and learn a policy from it. So the interesting question is, can we get there? Can we get the human performance here by just scaling the number of demos, right? Can we do that? I don't want to give an answer to the question because I don't know. Some people argue yes, some people argue no. But the problem is, in the near future, it's impossible to get GPT level data, high quality data for robotics, right? Like the amount of data we have in robotics is zero compared to data people use in training any language model. Okay, so what's the solution, right? How to build generalist robot with agility? How to get like something here? Of course, it is a super challenging problem, right? Every robotist's dream. I cannot tackle this question today, but I would like to share some recent thought with you today around this question. So in my opinion, on the agility axis, on the on the y-axis, the green axis, physics and dynamics really matters because that's the definition of agility, right? Agility means you need to treat the robot beyond just position control. You need to reason, right? The force, the torque, the dynamics, right? You need to reason F equals to ma. So the first idea of today's talk is better use of physics and dynamics, right? Essentially, can we combine learning with some structures and ideas from control and physics to achieve something I refer to as structured scaling? So on the generalist aspect, I think everyone agrees scaling really matters, right? You need to train the robot on many, many different data and many, many different scenarios and tasks. But the problem is not just how to scale, it's also what to scale, right? Scale what? So the second idea I want to pursue today is the better use of scaling. Especially, I think the robot learning community has been focusing too much on offline scaling, right? Either learning from demos or like Sim2Real RL. Maybe it is a good time to think about real life scaling, right? Can we combine offline learning with some real life learning via adaptation, planning, or like optimizations? Okay, this is like the philosophy outline, and the technical outline is here. So today's talk has two parts. The first part is relatively short, is humanoid whole body control using a technique called Sim2Real model-free reinforcement learning. The reason why I put in part one is Sim2Real model-free RL is a very straightforward way to combine physics, dynamics, and offline scaling. Because what you do is you train a policy in large-scale offline simulator, and the simulator is physics-based. And in the second part of today's talk, we're gonna give some hot takes or like retrospective thinking on Sim2Real RL. We're gonna discuss its fundamental problems and how to go beyond Sim2Real RL using learning control. Especially three hello ideas. Dynamics level, we don't want to do Sim2Real. We don't want to just do Sim2Real. Can we learn directly from the real world, right? Learn a word model, learn dynamics model from real world. And on the policy level, it's rather than end-to-end learning, can we add some structures? And the program level, can we use some ideas from learning to improve classic control paradigms like MPC? Okay, let me get started. The part one, humanoid whole body control via Sim2Real RL. So a represented project in this domain is called H2O, human to humanoid whole body teleoperations. So the goal of this project is we want to build an interface between whole body motion of human and humanoid. So the original motivation of this paper is from the movie Real Steel, right? If you watched, I watched the movie when I was a kid, and it's always a dream to kind of like real time translate, right, what we can do to what a robot can do. That's why we started this project in 2023. Yeah, and specifically, we wanted this interface support many different way to control humanoid, like a VR, RGB, or like a verbal instruction. And we also want to achieve some autonomy, right? Because once we have this control interface, we can integrate this interface with many high-level agent. Like you can do learning from demos, or you can do GPT for all, right? And finally, I want to mention everything I present today is open source. It's fully open source, from like training to deployment, yeah, to hardware deployment. Okay, before I talk about details, I want just want to play a teaser video. You can see in this video. Yeah, my student is wearing Apple Vision Pro to real-time whole body teleoperate the humanoid, right? And I want to emphasize this is not just upper body, it's a whole body teleoperation, right? We also control the lower body of the humanoid, yeah, and also the upper body and the fingers. And the humanoid walk to the bench and start doing some interesting task. Yeah, it is going to grasp a knife, but it doesn't going to hurt. It will not hurt you. Just cut a cucumber, um, and say hi to you, and step back and start sweeping the floor, cleaning the floor. Right. And at this point, you can see what the value of a whole body control, right? Because you have to move the base, right? You have to balance upper lower body, you have to support the upper body. Yeah. And finally, say hi to you again. And we have can achieve many things, like a lot of manipulation, working the plant, move basket, many sports, tennis, table tennis, and playing box, drawing letters, many different tasks. And this part is autonomy, integrating with GPT for all, do some humanoid interaction. And this is autonomous by integrating with diffusion policy, imitation learning. And finally, some robust it's verbal instructions. You can literally talk to the robot. Can you turn to the right? See you next time. Bye bye. The robot will respond. And finally, to publish a humanoid paper, you have to bully the robot to show the system is robust. So we did that. And outdoor locomotion is also pretty, the single policy, single neural network can also do a lot of outdoor locomotion. I'm sorry I played the video very fast, but if you want to know more, just check out the website. Okay, so how we achieve that? So before I talk about how we achieve that, why is it hard? So don't get me wrong, like teleoperation is nothing new. Right? Teleoperation has like 300 years history at least, right? It's nothing new. But why is hard for humanoid whole body? I mean, it is hard from two perspectives. From agility perspective, you need to solve a high-dimensional whole body control problem, right? Which require upper lower body coordination in real time, right? So in this video, the robot we are control has like 26-degree freedom, right? Not including hand, right? You need to solve a very high-dimensional continuous control problem in real time. And from a generalist aspect, you need to generalize to diverse human motion in real time, because you don't know which human motion you're gonna track in real time, right? You need to generalize to all of them. So how do we solve this in each tool? Sim2Real RL from large-scale retargeted human dataset. That's a one-sentence summary. Like Sim2Real RL from a large-scale retargeted human dataset. Okay, let's jump to detail. So there are two big steps. The first big step is to create a large-scale humanoid feasible motion dataset. So we start from a very famous human motion dataset called AMAS, corresponding to the first row. This is basically an archive of many mocap human motion data. You can see some examples here. Right? It's very diverse and very high quality. We have like over 10,000 like human motion clips here. But the question is, can we directly use that for training policy? No, because even though humanoid is already very close to human, they're still different. You sort of need to translate the human motion to humanoid motions, right? For example, the last motion here is absolutely impossible for H1 because the upper body of H1 is not that strong. It cannot support this acrobatic stuff, right? So we need some kind of like motion retargeting and some kind of motion translation. So we need the second procedure here. So the second procedure here is shape fitting. This is very straightforward. It's just inverse kinematics. So basically, we found a human model. It's called a simple model that is closest to humanoid. Is why the human model here is a little bit weird, because that is a geometrically closest model to the humanoid, right? Then we do a very simple inverse kinematics, and we call this shape fitting, right? You can see after this procedure, the second row, right, start looking a little bit closer to humanoid. But still, it is not enough because this retargeting is only kinematic level, right? It's only considered geometry and kinematics. It doesn't consider anything related to dynamics and physics, right? It's still hard to achieve by humanoid. So we need a third step, right? The third step we call is physics-based retargeting, right? The idea is still quite simple. What we do is we train a privileged imitation policy to imitate, to track all the motions in the second row using reinforcement learning. So we basically train policy in SIGEM using RL. The goal of the RL policy is to imitate to the second row, to track all the motions in the second row, right? The reason why I call it a privileged policy is because this policy knows everything. This policy is not sim-to-real. It knows all the state, everything in the simulator, because we want to filter out, right, impossible motions. We want to have a upper bound of what humanoid can do. Okay, and once we train this imitation policy, we use the rule out trajectory of the policy as the data set, right? The third row, right? The third row as the data set. This is basically rule out trajectories from the privileged imitation policy. So basically, to summarize, the goal of this procedure is to generate humanoid feasible motions, right? And filter out impossible motions like the last one. The last one we just simply move out. And finally, I think we kept like 90%-ish data from AMAS. So the humanoid is still very powerful, right? It can track 90% of AMAS data set. Okay, this is the first big step to create a large-scale humanoid feasible motion dataset. But again, this is only for simulation, right? You cannot to real this policy. So we need the second big step, which is fairly standard today, which is called a Sim2Real reinforcement learning based on teacher-student framework, right? So the goal is, right, we basically have a teacher policy, this privilege policy, right, in the ping policy. And remember, this privilege policy cannot to real because it's a privilege. You can see the input dimension, right? Real proprioception, it need like 300 dimension. And for motion go, it need 500 dimension, right? There's no way you can measure them in the real world. So what do we do is a fairly standard today, right? We first train this privilege policy, then we train student policy, the blue policy, right? By distilling from this pink teacher policy, right? The deployable policy, the blue policy, or like the student policy, right? Is pretty practical. It can to real because this policy only knows robot state available in real world, right? You can see the dimension here, right? The input dimension is only 63, right? Of course, it's conditional history, and the motion goal is only like 27 dimension. Yeah, and this is very standard. The distillations done by Dagger algorithm. So regarding the motion goal, we select the Sim2Real motion goal. The reason why it's 27 dimension is we only use 3 key points as a motion goal, like one head and 2 hands, and like each one is 9 variables. So together is 27 dimension. Yeah, because we want to make this framework general, right? We want this interface support as many devices as possible, right? Like VR. So we use a simple motion goal. And of course, as we can imagine, we use a lot of DR for robustness. Like DR stands for domain randomizations. All right. And again, what we learn is a whole body motion tracking interface, right? With the motion tracking interface, you can not only do teleoperation, you can also do like autonomy, right? For example, we can integrate GPT-4o with this interface, right? And integrating system 1 and system 2. In this video, right, GPT-4o real-time command, the humanoid, right? GPT-4o send high-level command to the humanoid, and our whole body tracking controller is going to follow GPT-4o's command. Yeah, we're using some multimodalities, so the input is text and image real-time. And the reason we have some delay here is we are waiting for the OpenAI API's response. It's pretty slow. Okay, this is like the first project, in the Sim2Real RL domain. And the second one, which is going to be super brief, is the opposite, right? Because I want to give you some examples of how hard like some examples of like reinforcement learning from scratch, how hard it is. So the previous examples, the H2O is learning entirely from human motions, right? We train using human motions in deployment time, or we teleoperate using human motions. So what if you learn some skill without any motion priors, right? And this project is called WoCoCo, stands for Learning Whole Body Control with Sequential Contact. Where the goal is we want to discover how reinforcement learning learn long horizon agile whole body skills without any motion priors, right? And without any motion prior, just from scratch. And we figured it's very hard to learn it from scratch. We need to decompose. The key idea of this paper is we need to decompose a long horizon skill into a sequence of contact goals and task goals. Due to the time limit, I cannot go into super detail today, but I want to play a video. This is like some parkouring we can achieve in simulations, again from scratch without any priors. And this is like some parkouring jumping, continuous jumping, and in real. And we can also translate some to the real, like this clamping, dance, damping. And also this we literally ask the humanoid to traverse on this cliff, right? And then the humanoid need to support using his upper body. And then finally is some local manipulation problem. The humanoid can move one box from location A to location B, right? So the key idea is, again, we need to decompose a long horizon skill into a sequence of contact goals and task goals. For example, for this parkouring, right, we can decompose the whole sequence to 5 contact stage. Right? We train a contact stage condition, contact goal conditioned policy. Yeah, unfortunately, I don't have time going into details, but the message I'm trying to convey here is even without motion priors, it's still possible to learn skills, but just need extra design in general. Okay, that is the first part of today's talk. I give you some examples of a Sim2Real reinforcement learning for humanoid body control. But the question I want to discuss today is, do we still need model-based control, right? Because all the demos in part 1 are trained with model-free Sim2Real RL, right? Without any, physics prior or whatever, right? And the video are pretty interesting. So do we still need model-based control? I don't know, but I want to give you some truths behind these successful demos, right? What happens in the Sim2Real gap? So in simulation, everything is pretty good. Something like this. If you still remember the agility generalist plot, right? Remember the x-axis is the task, the y-axis is the performance, right? Agility. And in simulation, it's typically something like this. All the tasks are pretty good. Maybe 1 or 2 tasks fail because like parameter tuning or PPO exploration issue or thinking issue, right? But in general, it's pretty good. However, we will transfer to the real world, like something like this will happen, right? Basically, all the task performance will drop a lot, even worse, right? Like some task that works very well in the simulation just completely fail in the real world. It happens all the time in my lab, all the time. Like because of Sim2Real gap, because of fragility to perturbation, stuff like that. So what's going wrong? Sorry, 1 second. What's going wrong, right? And I think there's some fundamental issues of Sim2Real RL. There are many, but I just want to mention a few, right? Like the policy are sensitive to training environment, number 1. And number 2, the Sim2Real gap is large, unintuitive, and hard to quantify, especially for some really nonlinear phenomena like gear backlash, slippage, aerodynamics, contact dynamics, blah blah blah. And right, it requires very tedious reward tuning, curriculum tuning, and the domain randomization tuning. The best method today is still GSD, graduate student descent, right? That's probably the only way. And it's hard to encode any physics priors and suffer from like poor sample complexity, and it's unsafe, of course. And finally, this is something I'm recently very interested. This framework doesn't give you test time improvement ability. Because once you learn policy from a simulation, policy is frozen, policy is fixed. Even though we know it's going wrong, it's doing something wrong in real world, we cannot further improve it, right? Yeah, this is some high-level limitations. So how do we mitigate them? A recipe I'm gonna propose today is learning control, right? Maybe we can actually have some control and feed this back, or we can get back towards, right? Particularly, there's three ideas I want to quickly go through today. The first one is dynamics level, right? Rather than doing entirely sim to real, can we learn dynamics from the real world directly? And the policy level, can we do some structure in RL? And the program level, right? Maybe we can use RL or learning to enhance classic control stuff like MPC. So in my philosophy, in my view, the role of control is threefold. First, it brings some structures and priors from physics, make everything more efficient, safer. And second, it guarantees or enhances safety, robustness, and efficiency. And finally, this is something recently very interesting to me, is control actually give you an interesting perspective for test time scaling, right? Like once you learn policy, we can use some tool from control for test time scaling. Like you can do online adaptation, online planning, online optimization, right? Okay, let's get started from the first one, dynamics level. Okay, so I did a lot of this work already in my PhD back in 2018. Uh, but at that time, I was pretty much learning shallow residual dynamics for simple system like quadrature, right? The idea is quite straightforward. You can see in this equation, the black part is well known, right? It's just rigid body dynamics. And the orange part is very, very confusing, right? It's very hard to know. This is like in general, like unknown dynamics, right? Something like aerodynamics for John. So the key idea at that time is we use a small neural network to learn this F term from real world data. Where the pipeline is very simple, right? We use a small neural network, F hat, to approximate this F function. And once we have F hat, we plug in the F hat into some nonlinear controller to get a policy, right? For example, you can use adaptive control or you can use MPC. And in general, if you care about stability and safety guarantees, you have to regularize F hat, right? You have to regularize the Lipschitz or something like that for stability guarantees. And here are some examples. Like for example, we can achieve a smooth drone landing. In your flight, we can do this real-time adaptation to wind conditions. And recently, we have learned dynamics as well. For area manipulation problem, the drone can draw in some letters on the wall. Yeah, but in general, for this line of work, we are learning a small neural network, right, to learn some residual dynamics. So after joining CMU, I've been thinking about how to scaling up this framework, right? Can we use a deep neural network, like transformer style network to learn directly from real world dynamics, right? And this project is called AnyCar. We try to learn universal vehicle dynamics directly from real world. In this paper, we learn a transformer-based deep dynamics model, and the model can adapt to different car, different environment, different state estimation method, all via in-context adaptation. Once we learn the model, we use sampling-based MPC for control. And this photo shows many different car, many different environment the system can adapt to. And I want you to pay attention to the white tear here. And this white tear is a 3D printed plastic tear, very bad tear, to stress test our model's adaptability. So here's some videos, and our model can enable like pretty precise control of drifting control in the wild. So the transformer can model drifting dynamics of unseen vehicle in the wild. Yeah, and this is like some adaptation to different slope, different terrain, and different slopes. And this is adaptation to an unseen like payload. The model didn't really know that the car is towing a big box and need to figure out everything real time online. Okay, how we achieve that? The model input output is quite straightforward. This is sequence to sequence prediction model. The model input is a k-step noisy state action history and h-step future actions. And the model output is h-step future state. It's basically a history condition sequence prediction model and parameterized biotransformer. And the key point of this paper is, as you can imagine, right, we learning this in the real world directly is very, very expensive. So what we do is we pre-train the model in simulation data and fine-tune the model in real world. And we collect a pretty diverse, large-scale real-world data is 100 million data point from very simple numerical simulation to WoCoCo to SXM, all the way to this F1 level simulation called Arthrotic Corsa. And this is a pre-training. And once we pre-train the model, we fine-tune this model in real world using like few shot, just 20K real world data point. Yeah. And this really makes this framework practical. And another thing to make the framework practical is the training design. Right? This is like our architecture, which is a fairly standard transformer. We have everything basically language model has. We have a tokenizer, kind of encode this original state action to a continuous latent space. And we learn the model in latent space. We have auto decoder. This is auto standard. But what I want to highlight is we actually have some design to make the model robust, right? We actually add random mascot and random Gaussian noise and random attack here, if you can see my cursor, on the history of state and action, right? All this robustness design is trying to mimic what's going to happen in the real world, right? Trying to make the model robust. Yeah, this really make this AnyCar paper scalable and work pretty well in the real world. Okay. Let's get some water. Okay, I guess you after these slides, you probably have a question, right? You know, I work on humanoid. You probably have a question. Does it work for humanoid, right? Can we learning a gigantic world model, right, or density model for humanoid and do control on top of it? We tried, and it seems like it doesn't really work, unfortunately. So this paper is called ASAP, just accepted by RSS. It's called Aligning Simulation Real Physics for Humanoid. So we found directly learning dynamics maybe is not a good idea for humanoid. Directly learning residual dynamics. I will explain why later, but in this paper, we propose alternative solution, which is learning a delta action model to match an sim and real, not learning a delta dynamics model. So the procedure is actually very straightforward. Let me go through the procedure first. We first pre-train a policy in simulation, the policy pi simulation, and we rule out this policy in real world, right? To get a sequence of state S, X in action A, and the superscript R stands for real world, right? We get a sequence of trajectory in the real world. And then we replay this sequence of action A in simulation. We get another trajectory XS. The superscript S here refers to simulator, right? And due to Sim2Real gap, right, the XS will be different from XR, right? Otherwise, the simulator is perfect, right? And then what we do is we train a delta action model, delta A, as a function of current state and the current action, right? This is like a neural network. Right? This is the closed loop function, right? It's not a sequence, it's a function, right? We learn function, learn delta A function, such that, right, in simulation, if you perturb, if you augment original action from real world by delta A, the resulting trajectory in simulation is close to the trajectory in the real world. Right. In other words, right, we're trying to learn a residual action model that bridge the gap between simulator dynamics and the real world dynamics. And this learning delta A is another reinforcement learning problem. The reward is just the distance between XX and XR. So once we learn this delta A model, as you can imagine, pi plus delta A, what happens in simulation is effectively equivalent to pi in the real world, right? So as you can imagine, once we learn delta A, we freeze delta A, and we fine-tune the policy pi. And finally, we deploy the pi in the real world. So in other words, you can really think of this learning delta A as learning sort of some, if you're familiar with something called iterative learning in control community, you can basically view this as a reinforcement learning approach for that. And yeah, it's basically delta A is trying to compensate the same and real gap in the policy space. And this is some examples of how it works. You can see in this video, the left is before we fine-tune the policy in delta A. You can see, I want you to pay attention to the ankle part of the robot. You can see it's a single leg balancing problem. The ankle is a little bit shaky, right? Right, you can see that I want to play the left video again. You can see that, you know, it can still do the single leg balancing, but just a little bit shaky. And the red one is with after we fine tune the model using learn delta A, you can see that it's much more stable. I know you probably have a lot of questions. Question number one is, can delta A generalize? The answer is yes. So the pi here actually cannot. We've trained a deep mimic style pi. So pi is specific for different tasks. But delta A is shared by different tasks. I guess your question number two is how many data required. And in real world, we only collect 8 minutes data. And this is why another reason we select delta A rather than delta dynamics, because it's much more data efficient compared to learning a residual dynamics model. I guess your question number three is how much delta A can help. Unfortunately, you cannot expect delta A works can totally solve a field motion. No, it cannot. It's more like making a motion perfect, making an 80% motion to 100%. You cannot expect delta A works very well for making 0% motion to 100. There's no way. The reason is we want delta A to predict residue very well around the tube, in a tube around the desired motion, right? If its motion is very far away from desired motion, we cannot really learn effective delta A. This is why in this video you can see the left video can still do single leg balancing. It's just not that perfect, right? And delta A can make it much better, but it cannot if the robot already fall for single leg balancing in the first place. Delta A probably cannot help too much. I don't want to overclaim, right? It's more like a iterative learning control, making everything more perfect kind of thing. Not like totally solve some from 0 to 1. And using this method, we can achieve this pretty agile whole body control. If you I play a lot of basketball, we can repeat like Kobe Bryant's iconic fadeaway jump shot, and this is actually slow motion. You can see we can coordinate upper and lower body. It's a very agile whole body control, and this is like a Cristiano Ronaldo's seal motion. The robot can do a 180 turn and jump and land and wave the hand, stuff like that. Yeah, check out more videos on the website. And everything's open source. From training, we're gonna open source the motion dataset as well and the deployment, Sim2Real, everything. Okay, I think I will skip this slide due to a time limit, but this slide is more like to visualize what delta A actually learn. By the way, for this framework, it's not only for Sim2Real, we also do a lot of Sim2Sim, right? We actually quantify a lot of result in Sim2Sim, but I will skip this slide. Okay, and the second level I want to talk about is policy level, and this is quite different from learning dynamics. It's more like learning a hierarchical and a structured reinforcement learning control policy. So the idea is maybe we can actually combine control and RL, right? We can do hierarchical RL and control. And this is one example in this video. In these examples, like a reinforcement learning policy, so only output centroidal level information, right? It only output the reference trajectory for the center of mass of the robot. And once we have this centroidal level reference, we have a low-level QP controller, right? Trying to optimize ground reaction force. And you can see we can achieve a very agile parkouring. The robot can continuously jump over obstacle. And here you can see as it can adapt, right? If the gap is too large, it decides to take an intermediate step. If the gap is within 80 centimeter, it's just one step jump. Yeah, you can see we can enable. I think for the first time we can enable continuous jumping of a quadruped over stairs, right? Again, this is a real-time video and continuous jumping pretty fast. And we can also the robot can also parkour over very tall obstacles. And we actually compare with the end-to-end reinforcement approach, and the conclusion is, due to the Sim2Real gap and other factors, and our method can enable much further jumping and much faster, and the Sim2Real gap is much smaller, require only a little bit domain randomization to make everything work in the real world. Okay, another thing to combine learning and control in hierarchical RL is safety, right? So this is also a very classic paradigm. We have a high-level reinforcement learning policy, which might be unsafe. And we have a low-level safety filter, right? Trying to filter out unsafe actions from our policy. right? This is like classic, pretty classic pipeline. So in this paper called Agile but Safe, we use a reachability-based safety filter, learn from a reach avoid value function, and trying to filter out this reinforcement learning policy. You can see in this video, the learn policy is simultaneously safe and agile, right? The robot can traverse very narrow corridor with collision avoidance guarantee by learning this filter value function, right? If you pay attention to this video, the LED, the green LED means the agile reinforcement learning policy is running. The red LED means we switch to the RL policy to a conservative recovery policy. Right, this is switching mechanism. The switching, the triggering is decided by a learn retrieval value function. Okay, I will skip detail today, but my point is hierarchical reinforcement learning control could be very important if you care about safety, if you care about efficiency, if you care about precision. That's my take. Okay, I want to spend a few minutes on the last part. This is the last part of my talk, probably 3 minutes, which is program level. How we enhance model protocol control using learning. So in case you don't know what is MPC, MPC is basically trying to solve this optimization problem in real time. And the main challenge of MPC is it's pretty hard to solve this problem in real time when the problem is highly non-convex or high dimensional. For example, contact ridge or nonlinear dynamics, right? Because in general, you need to take gradient, right? For the standard method, you need to take linear radiations, right? Like DDP, LQR, SQP, whatever. So an alternative solution is sampling-based MPC, right? Yeah. For example, for this problem, you want to throw a ball over the wall. The decision variable here is the angle you throw the ball, theta. If you plot, you want to throw the ball as far as possible. If you plot the landscape, this problem is not even continuous. You can imagine like gradient-based method will struggle a lot in this problem. And the sampling-based approach seems like alternative. One of the most famous example is called MPPI. In case you don't know what is MPPI, I just want to give you a 30-second tutorial. So MPPI is a sampling-based MPC method, which is actually very intuitive. So first, MPPI sample whole bunch of control sequence from a Gaussian, and the U is the mean, sigma is the covariance. And then we wrote these different samples in parallel simulation, right, to evaluate the cost functions, to evaluate the cost, like J1 all the way to Jn, right? They're just a bunch of scalars for cost. Right, once we have this cost, we compute the weight. Right, we use this kind of softmax stuff to compute weight, right? And the lambda is the temperature. Right, the smaller lambda you have, right, the more extreme, right, you are giving weight to the better samples. Right, this is pretty intuitive, right? For the better samples, you're gonna assign higher weight to it. For bad samples, you're gonna assign smaller weight to it. And lambda control how extreme you assign this weight. And finally, we compute output U plus using linear combination, the weighted sum of the samples, right, weighted by this cost, the weight. And this is how it works in practice, right? You can see this jumping problem. We can sample a bunch of trajectories. So because this MPPI is very parallelizable and is very flexible, right? We didn't assume anything about differentiability, anything, right? Even continuity. It is widely used in model-based RL as a planner. As an example is TD-MPC, TD-MPC2 from UCSD, right? Which is basically combined learned value policy prior and MPPI planning. And recently we have a follow-up paper called TD-MPC square, basically the TD-MPC2 plus policy constraints that gives SOTA performance in humanoid bench. It is much better than TD-MPC2 and the Dreamer and SAC in humanoid bench. I will not go into detail today, but my point today is MPPI works pretty well in practice. However, we don't have any theoretical understanding in terms of how it why it works and the convergence, etc. So recently we found a super interesting connections between MPPI and diffusion. It sounds a little bit weird. How can I connect something in control with gentle model? But it actually makes a lot of sense. To make everything complete, I need to define two notations. So P0 here P0 is a target distribution, right? It's a kind of PDF proportional to exponential to minus g over lambda. You can see here. And we want to achieve here, right? We want to achieve the maxima of this P0, right? Basically the optimal control point. And another thing I need to define is P sigma. P sigma is very similar to diffusion. It's a cropped version. It's a corruption version of P0, right? Basically, we convolute P0 and some Gaussian distribution, right? And get a P sigma. As you can imagine, the bigger sigma we have, the closer this P sigma is to nominal Gaussian, right? If sigma go to very large, and the P sigma is basically Gaussian. If sigma is very small, and this is very close to P0. It's just like very similar to diffusion, right? You convolute the original target distribution with sampling kernel, right? You get a noisy one. So what we found in this paper is we actually prove when a number of samples go to infinity, MPPI is literally doing diffusion. More precisely, MPPI is actually doing a denoising step, right? We prove the output of MPPI is actually one step score accent, right? Here, the green term, which is the gradient of log p sigma, is called score function, right? And then PPI is basically update your sample using one-step score function. And remember, the p sigma is a convolution between P0 and the Gaussian sampling kernel. So in other words, MPPI is roughly doing a denoising step, right? And if you compare this with score-based diffusion model and Langevin dynamics, you will realize they're very, very, very similar, right? In score-based diffusion model, you update the image in this way, right? The S theta is a learned score function condition on sigma, right? The only difference is MPPI, we don't have the last one. We don't have the SDE, the noise term, right? In score-based diffusion, we have this term. That is because in MPPI, you don't care about the coverage. You don't care about coverage. You only care about reaching the maxima. Another difference is the S theta here is learned. In MPPI is not learned. It's estimated using Monte Carlo from samples. Okay, once we realized this, we found MPPI didn't really do annealing, right? Annealing has proven to be very important for diffusion model, right? You need to sample from big sigma, from like more noisy distribution all the way to less noisy ones, right? And PPI didn't really do this. And once we figure this, we discover a new algorithm called DIAL-MPC, which stands for diffusion inspired annealing for lag MPC. The idea is actually quite simple, right? This is MPPI with large sigma, very fast to converge, but it's stuck, kind of like the convert to a wrong point, right? And this is MPPI with small sigma, right? This very close to original distributions, but it's got stuck in local minima. And DIAL-MPC is first we do large sigma, and then we anneal down to small sigma to get better boost words. And even better, we can integrate this with MPC because MPC is doing receding horizon, right? And then we can control the sigma of different time step in the receding horizon procedure, right? For the further future, we assign bigger sigma. For the near future, we have a small sigma. In such a way, right, we can do this receding horizon streaming diffusion, right? Because we don't need to do multiple diffusion step at a single step, time step, right? Because the whole sequence is doing streaming diffusion, right? And this is the last slide probably. And using these ideas, we can achieve end-to-end control, real-time or talk level control for full order dynamics, right? In these videos, for this jumping task, for example, we did not do any approximations. We didn't do any reduced order modeling, any local approximation, any quantification, or we don't even ask for predefined context sequence, right? It's end-to-end, right? The input is just some cost function, the output is torque directly, right? And because it's MPC, right? It's training free and plug and play. And compared to RL, right, we don't need any training, and also we only require like a few reward terms for each task, like 4 to 7, right? This is how it works for humanoid local manipulation, right? You can see the humanoid can push a box, yeah. So I guess a takeaway is right from control, like scaling online search, scaling online stuff is also powerful, right? Remember, for everything on this slide, there's no offline training at all. I think in the future, one thing will be really powerful is combine the online skilling here with offline training, right? Can we get best of online and offline skilling? Okay, I will skip this one, but basically we extend this framework to trajectory optimization. We can solve the push T task without any data, without any data, just from scratch. Okay, last slides. Just wanna summarize what I have been talking so far. So part one, I present whole body control using Sim2 reinforcement learning. And part two, we kind of talk about the limitation of Sim2 RL and propose some mitigations like dynamics level, policy level, and problem level. I think there are two takeaways today. First is this generalist aspect plot. I hope that's inspiring to some extent. The second is a philosophy that is structure scaling plus dynamics and physics. And finally, everything I talked today is open source. Check out my group's website for code and reference. Thank you so much. I'm ready for some questions, even though it's a little bit over time.
Thanks very much, Guanya. Yeah, as you can see, as I said, you can see Guanya's research really spans all the way from control to machine learning, from model-based to model-free. So yeah, I'm pretty sure this is very inspiring to our audience. So let's take some questions now, if Guanya doesn't mind staying online for a little bit more time.
Yeah, it's fine for me. Yeah.
Yeah. So are there any questions from our on-site audience? Okay, I see one popping. Well, I see many popping in a chat. I can read it here. So in the Delta action policy, what kind of data did you use to train that policy?
Very good question. Sorry, I apologize. Don't have time to read the details, but this is basically 1 second. Let me go to that slide first. Yeah. So we collect data in motion capture system. So the X here is actually the state of robot. It's the position, the kinetic pulse. Yeah. So you can imagine the data we collect is this X and A trajectory, the XR trajectory. And we put it in simulation, trying to minimize the distance between XS and XR. Yeah. So we need a motion capture system. But that'll be interesting to do a pure proprioception residual learning, the next paper. But this paper, we are doing state-based, like we calculating motion capture system.
Yeah, I think it's solved. And a second question, I think it's on humanoid control. Would the models be applied for interaction tasks like manipulation, manipulating objects, house cleaning? So I think that's asking how would you incorporate the objects into your
very good questions. My whole group is working on that now. By the way, it sounds very weird. I only have one product on locomotion now. It's hard to compete with industry on that, honestly. I think a lot of problems are solved. So I think the next thing I'm trying to do is local manipulation, which exactly tackles the question you ask, how to do interaction task. In general, it's much harder in my opinion. First, something like this in the video, right? You need the policy to be able to adapt to force. And second, you need to reason, right? The high level part, you need to reason how to establish the contact, when to establish the contact. And both are hard. Like from high level point of view, you need to leverage contact to plan contact. From a low level perspective, the policy need to adapt to contact force. Yeah. We are working on that right now. Yeah. Stay tuned.
Yeah, great. I also have a question on site. It's more specifically to the whole body teleoperation project on the humanoid.
Go ahead, Chenghao.
So people are asking, how is the locomotion teleoperated in your case, if you are using the Vision Pro?
Yeah, it's actually very simple. The representation in this paper with 3 key points. So like basically, we let the neural network figure out how to do locomotion. The input from Vision Pro is we get the head position and the hand position from the human. For example, if the human is moving forward, right? The neural network will understand, okay, I need to speed up to catch up. And if the head is going down and the hand is going down, the neural network will infer, okay, the human is doing squat and I need to lower the human line for squat, something like that. We let the neural network to figure out what human want to do from the history of the three key point. And also why three key point is really an engineering choice, honestly. It can really add more. For example, if you can also track the 2 feet, right? You can also track the torso. It's really a design choice. Yeah.
Yeah, I think there's a following up question on this. Um, so now you're using these key points to map from, say, human teleoperator to your policy input. Do you think this is the best interface such that your policy can generalize, or are there more general or more concise, say, motion space where your
Yeah,
policy
yeah,
can generalize way
yeah.
better?
Yeah, it makes sense. You asked the question, Chen Hao, because you're working on a lot of representation stuff. That makes total sense to me. I do not think Euclidean tracking is the best thing we should do. I definitely think something like learning latent skill, reuse skill, like something like ASE, pause, or like recent meta motival, that'd be the right way. Yeah, I'll be really excited to see more papers in this domain and open to collaborations. But because at that time we wanted to make everything well defined and make the problem formulation clean, so we choose Euclidean tracking. But I do not think that's the optimal way for sure. We need to learn a tokenizer or like something like that. Yeah.
Yeah, thanks a lot. And I saw questions popping up from the chat. Thank you very much for the talk. Um, this is a question regarding the delta action. Why is
Yeah.
it the same over
Mhm.
different tasks? You're saying this delta A model is learned across different tasks when it
Yeah.
incorporates a number of different errors, like different error dynamics, for example, in different tasks. How do you justify it's a general one?
Yeah, so we cannot prove it's a general one. It's empirically pretty general because the reason is shared across tasks. I think a lot of data is very simple. For example, like one of them we found, if you can see this figure, we show the magnitude of delta A for different dots. The ankle one is really significant because why it sounds funny, but like ISAC doesn't support closed loop mechanical chain. Connection. And in reality, G1 is that, right? Because you can think of delta here to learn kind of some inverse dynamics or whatever, right? And this is definitely shared. No matter what task you're doing, you always suffer from this. Yeah, and another example is like the real world motor maybe is weaker than the simulator, and the delta A also learns some motor dynamics, right? This part definitely are shared across different tasks. Is why we decide to train a single delta A across different tasks. Yeah.
Hope that answers the question. And I think another follow-up question. Yeah, go ahead, Guanya, if you want to add something.
Yeah, no, I'm reading the question from Mana. The question is like,
Yep.
why did I fine-tune pi plus delta A in simulation rather than directly deploy it? This is a very good question. I want to make it clear. The pi delta A only works in simulation. What you because again remember is once you learn delta A, the pi plus delta A is equivalent to pi in the real world, right? It's not the other way around. So delta A is not a residual policy. Delta A is not residual policy. It's different. Delta A is trying to align similar real. Once you learn delta A, pi plus delta A, the consequence is equivalent to pi itself in the real world. That's why we cannot directly, deploy pi plus delta A because delta A is not a residual policy. It's a model. Yeah, yeah. Because we need to fine tune pi, right? Because deploy pi in the real world is what we eventually care about. Yeah.
Yep. Also got another question on site. It seems so now we're talking about learning dynamics, learning world models. It seems it's well justified if we can learn such dynamics models from the real world data. But sometimes we realize actually for complex systems, it requires more data to train a good dynamics model to train a policy than directly use this data to train a policy. How do we justify this?
That's a super good question. I guess you have a background from manipulation. I agree, 100% agree. But I still believe model learning a model has some really irreplaceable advantage. Like the model you learn is cross-task number one. And if you directly learn action from human demos, you can never be better than human, by definition. But if you learn a model, right, you can do counterfactual reasoning. You can generalize different tasks. You can be better than human. You can do a lot of cool things, right? So, but I agree with you. How to improve like efficiency, how to make it like general, how to find a red representation space to learn a word model is definitely unsolved question. Yeah, and before that, before we know how the answer to the question, I agree. If you care about performance, if you have like some like 1 million data point, you should rather spend that for collecting high quality human demos rather than learning a word model. Yeah, but I do think word model has some really fundamental advantage over just learning action.
Yeah. And this is also a question that I got asked a lot. Like, since you may need more data to learn a good model, why would you not directly learn a good policy? But yeah, I think it's very well justified. Eventually, it's going to make a difference. Yeah. So
And
Guanya,
another take, because it's talking to the ETH, how to say, in academia, what we should do, right? Do you want to compete with industry that can collect way more data than you, right? We need to discover new paradigms. That's my personal take, right? And this is why I encourage, people working on like new stuff, right? Rather than, your skill, number of data. That's something like industry can do way better than us, right?
yeah. Okay, I think everyone here hears that. Yeah, and we were talking about the trade-off between generality and speciality, or the agility. Um,
Mhm.
we sometimes observe that we might have to sacrifice the performance on the specialist to get
Yeah.
a better generalist. And there's always a trade-off there. Where do you think is kind of the
I,
bar
I,
there?
I don't think it. Yeah, I don't think it's trade-off is fundamental. By the way, I think it's just our current pipeline cannot do them together. Like ask for even for your cat or like your 2-year-old infant human babies, right? They can do both pretty agile testing, right? In many different cases. I think this is really not fundamental. This is I don't think it's hardware fundamental either. I think today's hardware it maybe not Dex hand, but humanoid, trust me, I think hardware can do a lot of things very good. We just haven't figured out how to get agility and generalists together. Yeah.
And where do you think is the bottleneck? Do you think it's the network capacity, or do you think it's the
No, I think
representation?
I don't know. I today I give some angle, but I think the bottleneck in my opinion is we really need real life learning. Like I think one of the take is we all the human. I don't think you memorize all the skills in your offline brain. No, I think you adapt. You adapt. Human can quickly learn from few demos or quickly can activate some part in our brain. You have some offline pre-training part, I totally agree. But you cannot rely on like memorization or like offline learning for all the time. We have to think about real life learning. That's my take. Yeah. That's what I believe. Of course, like data is we haven't got a lot of data, neural network architecture maybe, and simulation quality, all these things. But I really think we need to do real life robot learning.
Yeah, we got another question from the online chat. So could you elaborate more on what do you mean by structured scaling? What structures are referring to now?
Yeah, like structure means like, it's a little bit vague, honestly. But structure means, for example, we can do pre-training in Sim, fine-tuning real world, not just from scratch, or in the ASAP, for example. Or the structure refers to you need to think about what you actually learn, right? You learn a residue action model, and it's more clear in this like quadrupedal stuff, right? Structure means maybe we don't want always end-to-end learning, right? It's good to combine something like model-based control, right? Like here, the QP, right? Or like safety layer. But in general, structure here refer to, I don't like the word inductive bias, but it's more like how do you like encode some priors from the real world to our learning paradigms, to our learning procedure. But of course, I agree. This is like vague definition, and I don't claim this is optimal. But I think again, I fundamentally believe you don't need this. If you have like infinite data, like GPT data, you don't need inductive bias. You don't need a structure. I actually believe that. I actually believe that if you have like GPT level data for robotics, you don't. But we don't have GPT level data. It's not even close. Before we have the next robotics winter, like the patient from general audience is limited, from VC is limited. I think we need to have structure. Because you don't want to wait for GPT level data for robotics. We have to embrace structures. Yeah.
Yeah, and
Okay.
another one regarding the ASAP project. You're mentioning it's not a good idea to learn humanoid dynamics for example, and
Mhm.
what are the thoughts behind? Since we
Yeah,
can't.
we try. Check out the paper. We actually compare. Again, I think if we have enough data, we could. But the fundamental reason is learning a reduced dynamics is hard because it requires a lot of data. I think Chen Hao also has some great work on that. And you really need to carefully design the architecture because you don't want the neural net overfit. Because it like the humanoid is context rich problem. The dynamics is not even continuous. If you naively through a transformer, the neural net will absolutely overfit to small noise. And remember, we're gonna do RL on top of that. RL will 100% exploit whatever is overfitted in the learned dynamics. But
Yeah.
again, if you have good design, if you have enough data, I will vote for that because it's more general than delta A for sure. But a problem is here in this paper, we don't have like hours of data, and there's no way you can train a proper dynamics model. Yeah.
Are you also looking into the method to quantify the uncertainty of the model and use that uncertainty
Yeah,
as.
yeah. That's a good we haven't, but that's a very interesting point. Yeah, that's very you can do a Gaussian process or whatever other conform prediction to make the reinforcement learning aware of the uncertainty. It'll be very interesting.
Great. Thanks a lot. Let's wait for one last question, if there's any. Okay, like especially from online. Do we have any questions on site? Okay, I guess we got the last one. If we use the classical dynamics models plus something like a delta or error function, I guess it's like a residual policy, do you think that's
Yeah,
going to be helpful if we use real
Yeah,
data?
yeah, we haven't do that because for humanoid, it's really hard to analytically write down the classic dynamics model or classic control. But for quadrature, we did that, right? For quadrature, for example, here we learn the way we learn reduced dynamics is not on top of something like Isaac or WoCoCo. It's on top of a classic Euler-Lagrangian equations, right? You can definitely do that if everything is analytic, right? And also for the policies, it's similar, right? We have analytic policies. But for humanoid, if you want to write down like 20,000 codes C++ from Petersburg out to you can do that, but it's really hard. Yeah, yeah. Anyway, I have to go. Thank you, everyone. Yeah,
Yeah,
and if you have more questions, feel free to email me. And all the references are here. Thank you so much. Yeah.
yeah.